마지막 내용 간단하게 설명만 조금 더 하면, 한글로 하면 그 어널리시스 하면 시스템상으로도 그렇고 굉장히 아이디어랑 컨버션을 만들어낼 수 있으면 오토사이클이 무조건 좋습니다. 무조건 좋고 심지어 환경에 피해도 적고, 컨버션이 다 된다는 얘기는, 컨버션 한 번에 동일한 조건으로 다 된다는 얘기는 사실 굉장히 여러 메리트들이 있어요. 나중에 가스터빈에서 사실 그런 파트들 설명드릴 일은 없을 것 같긴 한데, 가스터빈도 사실 디젤 사이클과 거의 비슷한 유사한 특징을 가지고 있겠죠. 그 가스터빈이라고 하는데 유동이 계속 들어가서 나가는데 거기에 유동을 아주 균일하게 온도를 한 번에 컨버션 시킨다는 불가능하기 때문에 가스터빈도 문제가 많습니다. 가스터빈도 뭐 낙스나 삭스 문제가 있고, 고온에 가면 뭐 질소산화물 같은 게 좀 만들어져서 그것도 문제가 있고, 그것 때문에 이제 고온 부품을 엄청나게 힘들게 개발해야 된다는 것도 있는데, 그런 점에서 이제 한 번에 컨버션을 다 완성시킨다는 건 되게 엄청난 기술이긴 한데, 계속 얘기지만 저희들이 이 컴프레션 레이쇼를 늘리려면 아주 작은 볼륨에서 만들어진 고온 고압의 가스가 한 번에 이걸 다 터트려야 되는 건데, 익스펜션 할 만큼 그게 일단 생각해보면 쉽지가 않고요. 그게 일단 쉽지가 않고, 그래서 뭐 림번, 리치번 해가지고 뭐 여러 시험들을 많이 하게 되는데, 그게 일단 쉽지가 않고, 그게 기술적으로 거의 불가능하기 때문에 대형 선박 혹은 뭐 좀 사이즈가 크다 혹은 워크가 크다 싶으면 다 디젤 사이클로 넘어가고, 아까 잠깐 EV카 관련해서 말씀을 드렸는데 뒤쪽에 아마 제 자료를 넣긴 했을 텐데, 브레이크 사이클 관련해서 인터널 컨버션 엔진이, 그러니까 보통 어떻게 생각하냐면, 뭐가 브레이크 사이클 한 40% 효율 얘기하면 이쪽 저 오토 사이클하고 디젤 사이클은 20% 얘기합니다. 그 서머 에피션시 그 연료부터 계산을 하면, 뭐 최근에는 사실 기술이 많이 올라가서 뭐 일본 같은 경우에는 서머 에피션시 뭐 45%, 50%까지도 얘기를 하긴 하는데, 뭐 그건 일본의 얘기고, 우리나라 같은 경우에는 30, 2, 3%가 맥스인 것 같아요. 이 오토 사이클이나 디젤 사이클 관련해서. 근데 이게 되게 작아 보이는데, 배터리 잘 생각해보면 배터리가 문제가 뭐냐면 에너지 덴시티가 너무 낮습니다. 저희 그 사용하는 가솔린이나 이 디젤 엔진 연료에 비해서 너무 작아요. 그 지금 브레이크 사이클이 사실 가장 이제 단위 볼륨당 혹은 단위 구성하는 질량당 가장 많은 에너지 출력을, 아웃풋 퍼포먼스를 낼 수 있는데, 그게 대략 한 배터리 50배 정도 됩니다. 뭔 얘기냐면 그냥 똑같은 연료 넣고 비행기 띄우면 50배 더 날아갑니다. 그게 이제 지상 같은 경우에는 사실 그거를 감안하더라도 할 만한 가치가 조금 있죠. 뭐 환경 문제를 줄인다고 하는 뭐 논리도 있고, 뭐 여기서는 사실 차가 중간에 멈춰도 일단 100% 죽는 건 아니잖아요. 차가 가다가 멈춰도. 근데 비행기 같은 경우에는 이제 가다가 멈추면 뭐 추락하거나 혹은 전쟁 중에 가다가 추력을 멈추면 이게 문제가 크기 때문에 쓸 수가 없습니다. 그리고 뭐 하이브리드 얘기도 나오는데 뭐 그것도 쉽지 않은 것 같고요. 그래서 뭐 인터널 컨버션 엔진이 뭐 다 망했다, 뭐 어쩌고저쩌고 하고 뭐 다 배터리를 바뀔 거다 하지만, 조금 이쪽 상황에 좀 듣다 보면 여러분들이 은퇴할 때까지는 안 바뀌지 않을까 싶습니다. 일단 제 생각에는 여러분들 은퇴할 때까지는 세상에 이렇게 획기적인 일이 확 발생하지 않기 때문에 디젤 사이클이든 인터널 컨버션 엔진은 계속 있지 않을까라는 생각입니다. 뭐 이거는 개인적 사견이고 지극히. 네, 두쪽 필드에서 있는 얘기를 다 들어본 입장에서는 한 3, 40년 남지 않았나 싶은데, 그래서 so let's try to solve the problem. One of the problem examples 9.2 explain about the diesel cycle. So this is a diesel cycle, and there is no description about the cold air standard analysis. So just air standard diesel cycle. So which means that so we can utilize the cold air standard analysis directly for solving this diesel cycle problems. So I tried to separate the two ways to solve the problem. The first thing is that either gas table, and the second thing is that the cold air standard analysis. So in the description, the compression ratio is 18, T1 is 300 Kelvin, pressure is 0.1 megapascal, and cutoff ratio is 2. In that case, to determine the whole of the procedure, the temperature and pressure value, and the second thing is the summary efficiency. The third thing is that mean effective pressure. Mean effective pressure, I already said that's the volume change. I mean the W net over the volume change. So 3, 4, P and T. This is 0.1 megapascal. This is 300 Kelvin, and this is the third point. So in order to solve this problem by utilizing the ideal gas table, then we need to check that the relative volume, relative specific volume, and the relative pressure value to solve the problem. This is just coming from the table. So 1.3861 and VR1 is a 621.2. And then in order to get this process 1 to the 2, we know that the compression ratio, which means that VR2 over the VR1 are the same with this volume ratio before and after the V1 over the V2 over the V1. Oh, 2. Then, which means that VR2 is 1 over R, which value is 34.51. Similarly, P2 over the P1. And next thing is that based on this value, by interpolating this system, so T2 is equal to the 890.3 Kelvin. Interpolation 34.51, determine the 898.3 Kelvin, and then H2 value is 930.98. PR value is also determined at 74.75 by interpolation of this specific volume or relative specific volume or the temperature or whatever. So you can utilize several kinds of things. So then, based on the pressure ratio, over the PR1, R1, which means that P2 is equal to the 9.393 megapascal. So 9.393 megapascal. Then, in order to get the information, so in this problem, there is no information about the highest temperature value because we can solve this problem by only considering the ratio of the temperature. So 2 to the 3, we know that P2 are the same pressure as the P3 because this is the global assumption to solve this diesel cycle, which means that 9.393 megapascal is the primary consideration of this problem. So, in case of the Otto cycle, we're starting from the T3 in order to solve this problem, and in case of the diesel cycle, the starting point of this problem is pressure is 9.393 megapascal. Then T3 is V3 over the V2 multiplied by the T2. This is coming from the ideal gas law. So which means that 1796.3 Kelvin. It's because this is the color ratio. This is already get the information about here. So we can get easily this problem answer about that the 1796.6 Kelvin. So from here, H3 is 1991.1 kilojoule per Kelvin. VR3 is 3.97. PR3 is 1299.868. This is just the evaluation of this table value of the 1800 Kelvin. Then we rearrange out this value. This is 1796.6, and VR2 is VR3 is 3.97, and this is the 1299.868. This is the 1991.1. Then we try to make some additional process about that 3 to the 4. The first thing is that VR4 over the VR3 are the same as V4 over the V3. But we cannot directly get the information out of this ratio, because in the Otto cycle, this ratio is just considering that the compression ratio. But in this problem, so we know that the V3 is not directly connected with the compression ratio. There is some additional information of this cutoff ratio in order to solve this problem. So, which means that VR3 VR4 is equal to, the first thing is that V4 over the V2 at first, and then we separated this V2 over the V3 simultaneously. So this is related to the cutoff ratio, and this is related to the compression ratio, because V2 is the maximum volume of that this system, and V4 is the minimum volume of this system. So in VR3. So this meaning is that RRC VR3, which means that VR4, this is our the primary goal to solve this problem is 35.73. And after that, similarly, by calculation of this problem, T4 is 87.7 Kelvin. U4 is 664.3 kilojoule per kilogram. PR4 is 71.1. So this answer, this PR4 is utilized for the P3. PR4 over the PR3 is equal to the 0.296 megapascal. in the ideal gas table, if you can get some one of the information related to the temperature, specific internal energy, or pressure, relative pressure value, or relative specific volume value, or temperature value, among them, the one information can determine the one of the specified state when you utilize this ideal gas table. So we rearrange after this problem. So what the chance? This is a 0.296. This temperature is 887.7. PR2 is 7.41 and 35.73. And the H value, U value is 664.3. Maybe U1 is 4.07. So maybe this is the problem A's answer sheet after this problem. So based on that table, we just put in the sub values for solving the problem. So summary efficiency is U4 minus U1, H3 minus H2, so which means that 576. MEP is W cycle over W1 minus B2. When you divide by like this, W cycle over M, V1 over V2, and also we can change that this equation over M is V1 1 minus 1 of R. When you put the whole values, the first thing is that W cycle over M is H3 minus H2 minus U4 minus U1, which value is 617.9 kilojoule per kilogram. V1 is R T1 over the P1, which value is 0.861 cubic meter per kilogram. Finally, MEP is 0.76 megapascal. Maybe this answer is more precise than the cold air standard analysis, so we need to compare the value of this cold air standard analysis. So this is the ideal gas table, and this is the cold air standard. Analysis. So maybe summary efficiency is quite easy. But in order to determine the whole of the procedure, then we need to determine the pressure and temperature by utilizing several the ideal gas relation about that the P1, P2, or P1 over the Q2 over the T1 is the P2 over the P1 case minus K1 over case or whatever. So cold air standard analysis. The first thing is that from 1 to the 2, T2 over the T1 is P2 over the P1, K minus 1 over K. And similarly, V1 over the V2, K minus 1. So, which means that this is the compression ratio of this problem. So this K value is a specific ratio. Specific ratio is, in case of the error, is just 1.4. So which means that T2 is 953.3 Kelvin. P2 is 5.79 megapascal. And the second thing is that P2 is equal to P3, so which means that this value is at 5.79 megapascal. T3 is V3 over the V2, T2, which means that 1906.6 Kelvin. 3 to the 4. By comparing the utilization of the ideal gas table, equation is much simpler than before. T4 over the T3 is V3 over the V4, K minus 1, RC over R, K minus 1. So which means that T4 is 89.90 Kelvin. P4 is P3 multiplied by the T4 or the T3, Q over K minus 1 is equal to the 0.311 megapascal. So we write down the answer about the P and T, such as this is the same 0.1300 Kelvin. This is the 5.79. T is equal to 953.3 Kelvin. The other thing is that 5.79. This is a 1906.6. This is the 8.29.9. This is the 0.3 or 3. 9.9, 2.311. So, due to that overestimation of the state 3, summary efficiency is 0.614. MEP is 0.76 megapascal. So which means that the first thing is that calculation procedure is much simpler in case of the cold air standard analysis. But the point is that we do not reflect the variation of the specific heat above the 800 Kelvin. As I think that, so when you check that the table below the 800 Kelvin during that process, then maybe the error bar is much smaller than the higher temperature. In the table, usually, so 800 Kelvin is about to the maybe the error range is about to the 1 or 2% between that the ideal gas table and the cold air standard analysis. However, above the 800, and there is a deviation happen between that the CP value and CV value. The ratio of that the two value are continuously increases, and then finally, so above that the 1000 Kelvin, that large deviation happen with some ambient condition of the specific heat. So for this reason, above that, in this case, some values are above the 800 Kelvin, so which means that large variation of the specific heat difference induces the error between that by comparing the ideal gas table and the cold air standard analysis due to that, to this reason. Okay, then this is the internal combustion engine, and there is a Stirling engine. A Stirling engine is a combination of this process, so maybe your cycle, we do not care about that your cycle, because the internal combustion engine is only focusing on that the diesel cycle and the Otto cycle dominantly. So we move to that the gas turbine engine, gas turbine power plant for this procedure is much better to understand of the chapter. So this is a gas turbine. I already said to that. From the left side to the right side, the air continuously goes through the compressor, combustor, turbine, and finally that goes out from this engine. The most important thing is that the first thing is that in order to design this system, I already said to that. So in case of the cycle energy balance, every kind of the system is cycle energy balance. There is a system. There is a Q in, Q out happen, and then between the difference between the Q in and Q out value, W cycle always happen. So by comparing between the two things, the Q in happen at the combustor. So in here, combustor is combustion chamber, so combustion chamber, combustor, whatever, it doesn't matter. So in case of the Q out, so in this system, there is no Q out happening in the power plant system. And also in case of the aircraft system, there is no Q out value component because this is utilized for the artificial heat exchange by utilizing the large reservoir of air in this system. I mean, ambient condition of this air system is utilized as some heat exchanger. So we simply think about it. So when you take some airplane, there is only inlet and outlet exists. There is no additional pipeline behind this rotary engine, and then there is no pipeline to make it some heat exchanger. We just throw out the whole of the energy, just go out to the ambient condition, ambient system, and then after the cooler air comes in front of this engine cycle. So which means that we can imagine that the whole of this world is heat exchanger, and reservoir meaning is that we make a some large of the Q value just adjusted to the ambient condition. However, there is no temperature change during the process because the volume of this whole of the world or whole of the air system is much larger than this exhaust gas. So for this reason, there is there is no device about the heat exchanger in here for substituting this Q out value. But the point is that heat exchanger is similar to that of the air, ambient condition. And then this W cycle is two things. The first thing is that W out is happen to the turbine system, and air comes into here, that is originated into here, but the starting from this origination condition, then we try to make this higher pressure value in order to satisfy the high potential of this workflow. So, which means that there is W in happen at the compressor. And similar to that of the previous problem, so we can also utilize the cold air standard analysis before designing the whole of the gas turbine system. But the point is that how to consider that the combustion gas. At this semester, we do not consider that this combustion process because that is totally different from and I think this is a totally different process compared to this power cycle itself. So maybe as I think that the combustion is also one of the state of the art of the mechanical engineering, and then it is impossible to control the entirely to make it some appropriate amount of the energy to in value from the fuel with the mixture of the air. However, we can know that we can simply approach that by utilizing the mixing law or some chemical reactions, and then chemical reaction enthalpy value. Then we can calculate that this procedure, then how much of the temperature is reached during the combustion at the second semester. So when you I'm not sure that, so when you will take the apply thermodynamics, and at that part most of contents is directly related to this combustion process. So if you have some loss of interest related to this combustion process, then I strongly recommend that this apply thermodynamics. So this is also based on my experience to take to apply thermodynamics. Okay, so we simplify this air standard Brayton cycle as shown in the left figure. So air comes into the compressor. The compressor makes some high pressure here with some isentropic compression. And after that, in the combustor, similar to that of this diesel cycle, there is some slight volume change happen during that process. But during that process, I already said that in case of the heat exchanger, actually there is a pressure drop happen during the process, but during that process, pressure drop by comparing the state of the magnitude of the pressure drop value is negligible compared to that originated value. So, which means that P does not change during the process. P is constant from the 2 to the 3, and after that, isentropic expansion happen at the turbine system. This is the work output value. This is the Q in. This is the W in. And finally, we do not utilize this heat exchanger, but we can assume that, okay, so heat exchanger, there is an artificial heat exchanger exists, and then there makes some Q exhaust value happen at the heat exchanger part. So then, different from the previous internal combustion engine. So this cycle is only operated by the open cycle. In case of the open cycle, we utilize an enthalpy value based, because mass flow comes into the control volume and mass flow goes out from the control volume, then always flow work happen, which means that we should change that framework from the specific internal energy to the specific enthalpy value. So this equation is quite simple. So this is a TS diagram. There is a turbine is making some difference between the H3 minus H4. So maybe the result assumption is open system, adiabatic condition, isentropic, negligible effect, kinetic potential energy variation. So this is also explained in the section of the chapter 4. At there, I already explained that. So in case of the turbine and compressor is based on that assumption, then we only consider that the enthalpy change during the process in order to make some cycle analysis. But if we analyze that this Brayton cycle application are two things. The first thing is that power plant system. In case of the power plant system, we can ignore that the velocity change of this system, but in case of the aircraft system, the outlet kinetic energy is also very important in that case, because outlet velocity is determining the value of how fast of that aircraft system. At that time, I re-explained about that. At that time, we should consider that the velocity difference before the inlet and outlet velocity. So anyway, so compressor is the difference between that H2 minus H1 value, and this is the combustor. Combustor is difference between that H3 minus H2, and these two kinds of things are the same. Heat exchanger. This is the turbo machinery. So much. This is the W in and W out. W in and W out. This is the heat exchanger, and then which means that H4 minus H1 is a Q out, and H3 minus H2 is a Q in value. So equation quite easy. So thermal efficiency is the same. So thermal efficiency is the Q in value is here, H3 minus H2, and here is a Q out value, which is the same as a Q turbine, and this is the Q. Sorry, Q not Q in, Q in, Q W out, W in. Turbine, W in value is WC, and this is the Q in value is the same as a combustor, and backup ratio is this is the QC over the Q. WC over the WT. So the question is, in case of the Rankine cycle, we usually do not care about the backup ratio. Backup ratio is almost 0.02 or 0.03, which is only the percent of the 2 or 3%. But in case of the Rankine cycle, this is one of the biggest advantage of this cycle. Compressor energy also containing of the compression work of this air. So in case of the pump, we do not care about that the volume change, because in case of the leaky side, we assume that okay, so isentropic process, that there is no volume change. We can only consider that the V multiplied by the pressure change here, when you calculate this pump work input value. But in case of this Rankine cycle, for the compressor, so it is, we should consider that the simultaneously about that the volume change and the pressure change value in order to calculate this compressor value. So usually, in case of this Rankine cycle, the backup ratio is almost 30 to the 50% of the turbine. 50%. I mean, the compression work is 1/2 of the turbine work output. So, which means that at the same temperature, I mean the same highest temperature of the Rankine cycle and the Rankine cycle efficiency is always smaller than the Rankine cycle. So for this reason, human beings try to achieve the highest value of the thermal efficiency by utilizing this Rankine cycle, because Rankine cycle, there are lots of the advantages of this Rankine cycle, because the first thing is that we can increase the temperature as much as possible by controlling the appropriately for cooling some materials and others, which means that based on that the Carnot cycle, 1 minus Tc over the Th. Tc usually the T ambient condition is about the 300 Kelvin. In case of the water system, when you try to increase the thermal efficiency of this Rankine cycle, then maybe upper limit of this temperature is around the 700 Kelvin, 700 degrees Celsius. Which means that above that the 700 degrees Celsius, the water is usually decomposed, changing into that the hydrogen with some oxygen. So which means that it is impossible to increase further the temperature of the Rankine cycle, even though that this system efficiency, the Rankine cycle system efficiency is quite powerful. However, in case of the Rankine cycle, when you control the combustion behavior, this temperature in case of the Rankine cycle, the H2O temperature is limited to the utmost 800 degrees Celsius, but in case of the Brayton cycle, ideally, this air cycle is the lower temperature of the material. So for this reason, due to the limitation of this Baroque ratio, I mean the large variation of large amount of the decompression work, the mechanical engineer trying to develop this Brayton cycle further and further and further. Finally, this Brayton cycle operating temperature is 1,800 Kelvin, compared to the Rankine cycle is about to that the 1,000 Kelvin. 한글로 이걸 좀 설명을 드리면 어차피 수업은 여기까지 하면 될 것 같고, 가스터빈 엔진은 두 가지가 좀 특징이 있는데, 하나는 저희가 힐 익스체인저를 달지 않습니다. 네, 힐 익스체인저를 달지 않아서 랭킨 사이클과 달리 가벼워요. 뭐 설명을 뭐 영어로 하면 주관도 까먹기 많아서. 참고로 제가 한글 요약할 때가 아닌데 한글로 수업할 때 대비해서 영어로 수업을 하면 한 20%는 더 나는 것 같아요. 설명을 한글로 하면 사실 설명이 더 많은데 제 영어 실력이 한계겠지만 그 부분을 이해해 주시고, 그래서 랭킨 사이클 대비해서 이 히트 익스체인저를 달지 않아도 된다는 엄청나게 큰 강점이 있어서, 그래서 브레이튼 사이클은 설치도 쉽고요, 어딘가에 설비하기도 쉽고요, 비행기에 탑승시키기도 쉽습니다. 대략 설명을 드리면 랭킨 사이클로 거의 동일한 브레이튼 사이클과 거의 동일한 퍼포먼스의 출력을 내려면 물을 한 몇 톤씩 들고 다녀야 돼요, 비행기에 하려면. 그래서 옛날에 굉장히 많은 랭킨 사이클들이 먼저 개발됐으니까 많은 시도들이 있었는데도 불구하고 가스터빈으로 모든 에어크래프트 시스템이 넘어간 가장 큰 이유이기도 합니다. 그래서 그게 가장 큰 요소 중에 하나고요. 그래서 이 전체 모든 세상에 있는 그 에어 시스템 자체를, 에어가 존재하는 거를 힐 익스체인저로 쓴다는 게 사실 가장 큰 강점이고요. 그래서 저희가 똑같이 두 개의 힐 익스체인저, 두 개의 워크 인풋과 워크 아웃풋 컴포넌트를 가진 이런 시스템을 구성하게 되면 이퀘이션 자체는 굉장히 심플합니다. 이퀘이션 자체는 오픈 시스템이고, 저희들이 이제 오픈 시스템이 됐다는 얘기는 엔탈피로 다 계산한다는 얘기고, 이 계산 방법은 이전에 6단원 전에 얘기했던 그 컴포넌트 어널리시스보다도 훨씬 쉬워요. 뭘 하든 H1부터 H4까지만 보면 어떻게든 답지가 나오는데, 이 뒤에 잠깐 설명드렸던 얘기 뭐냐면, 그러면 실제 이피션시 어떻게 되냐라고 궁금하잖아요. 왜 도대체 텀이 맞느냐. 원래는 맨 처음에 개발됐을 때는 이 브레이튼 사이클의 용도 자체가 발전 사이클이 아닙니다. 좀 달라요. 랭킨 사이클은 애초에 만들었던 목적이 메카니컬 동력을 파워 사이클로 그걸 하기 위해서 만들었던 건데, 브레이튼 사이클은 용도 자체가 애초에 에어크래프트 시스템 혹은 배에 들어가는 이런 퍼포먼스를 내는 터빈 쪽에 일만 고민하는 거를 주로 많이 진행했었던 걸로 저는 이해하고 있습니다, 역사적으로. 왜냐하면 요 백업 레이시오라고 하는 요 컴프레서 워크가 전체 터빈에서 생산되는 일의 한 30-40%를 잡아가요. 그래서 이 컴프레서 워크가 없이 터빈만 하면 출력이 엄청나게 큰데, 터빈에서 항상 컴프레서 쪽에서 항상 엄청나게 많은 에너지를 가져가기 때문에 실제로 출력되는 일은 브레이튼 사이클의 동일한 온도대, 그러니까 동일한 저기 위에서 보여드리는 TH 값이라고 하면 최소 10에서 20%가 빠집니다. 10에서 20%는 넷 기준이에요. 예를 들어서 랭킨 사이클 40% 나온다고 하면 브레이튼 사이클 똑같은 온도에서 계산하면 20%밖에 안 나옵니다. 그런데도 불구하고 몇 쓰냐면, 저 위에 간단히 설명드렸지만 랭킨 사이클의 워킹 플루이드는 물인데, 물 온도 800도 넘어가기 시작하면 H2랑 O2로 분리됩니다. 그 이후부터는 랭킨 사이클이 아니에요. 그거를 잘 불 붙여서 차라리 딴 걸 하는 게 낫지. 이제 그때부터는 그렇게 되기 때문에 이제 원자력 쪽에서 항상 HTR에 대한 니즈가 있는데, 원자력 쪽도 이제 발전이 거의 끝났다는 얘기기도 하고, 랭킨 사이클 올라갈 수 있을 만큼 지금 온도를 거의 높인 상태입니다. 지금 가장 높은 이 랭킨 사이클 발전 실제로 실증은 한 760도 정도 되는데 그 이상은 없어요. 그 이상은 이제 기술 개발이 없고. 그런데 반해서 브레이튼 사이클은 저희가 머터리얼의 한계, 그러니까 거기 안에 재료가 여러 가지 이제 오퍼레이션을 들어갈 텐데, 그 머터리얼만 잘 한 개치만 높여주면 거기까지 올릴 수 있습니다. 그래서 만약에 저희가 뭐 어떤 수단과 방법을 안 가리고서라도 2000켈빈 만들게 주겠다? 그럼 2000켈빈 만들 수도 있어요. 그래서 그런 잠재력을 아마 그때부터 왔어서인지 그때 굉장히 효율이 낮음에도 불구하고 계속적으로 개발이 됐었고, 그래서 현재는 브레이튼 사이클 단독으로만 했을 때도 랭킹 사이클하고 비슷하고요. 한 40, 뭐 5% 정도 나온다고 알려져 있고, 지멘스나 이런 데서 공개된 거 보면. 여기에는 이제 지금 당장 설명 안 드렸지만 저 4번 사이클에서 아웃렛 템퍼처가 좀 높아요. 여전히 한 1000켈빈 정도 될 건데, 걔를 잘만 쓰면 저 랭킹 사이클에 연결해도 되잖아요. 랭킹 사이클에 연결이 되기 때문에 걔를 같이 쓰게 되면 지금 기록으로는 4% 됩니다. 서머 에피션시가. 그래서 브레이킹 사이클은 이제 브레이트 랭킹 사이클이라고 하는 인테그레이티드 사이클이라는 발전이 계속 되고 있고, 그게 한 62%, 63% 실증됐다고 알려져 있고, 거기에 이제 저희가 이제 디스트릭트 히팅이라고 하는데, 지역 난방이라고 뭐 들어보셨을지 모르겠지만 그 지역 난방까지 같이 하게 되면, 물을 데워서 다시 저장해서 하게 되면 거의 한 70%, 72% 됩니다. 그러면 저희가 카나다 사이클 계산해 보면 85%가 맥스예요. 2000켈빈이면 85%가 맥스인데 75% 쓰면 대충 한 80% 정도 나오거든요. 이거 제가 랭킹 사이클 맨 처음에 설명할 때 말씀드렸는데, 카르노 사이클에 80% 정도 쓰면 진짜 다 쓴 거예요. 거의 진짜 나와야 되는 페어 빼고는 전부 다 활용한 수치라서 브레이튼 사이클로 지금 계속 사람들이 연구를 하고 있는 이유이기도 합니다. 물론 랭킹 사이클도 연구합니다. 랭킹 사이클도 계속 그 온도의 끝에 가기 위해서 계속 노력하고 있고요. 그래서 이따가 봅시다. 이따가 뒤에 계산은 이따가 합시다.